I looked it up because it kind of fascinated me. And now I've got my picture all wonky. There we go. This guy's called flux. So we're going to find this surface integral. So essentially, you're finding a double integral of a vector field over a surface, S, which would be this guy up here. Try and think of this as like a hanky, a kind of curved piece of space. And this is our new formula. This is another way in which you can calculate the surface integral. So you imagine you've got a region D on the XY plane. You project that up to the surface and you end up with this green guy called S. And the surface will have an equation that you can write in the form Z equals a function of X and Y. And this fella here, every single point of this, there is a three-dimensional vector F, right? A force field. And so the flux is measuring the total amount entering or leaving the surface S. So I looked that up, what does flux mean? And that's what you're talking about yesterday, Will, right? So when you evaluate this, don't you get the answer 42 or minus 42, right? And so when you're doing these guys, that's
the meaning of life.
Yeah, yes, meaning of life. So that's the total amount of whatever it is you're measuring in the terms of this situation here. So here is our first example. We're being asked to calculate this. The vector field is given as these three guys. And the surface Z is that, and it's between Z equals 1 to Z equals 4. So to be able to calculate this thing, we need to know P, Q, and R. P, Q, and R is what I call this guy, and this guy. Right? So in this question, P will be negative X, Q will be negative Y, and R will be Z cubed. So far, so good. You also need to know G, which in this case is actually pretty easy because G is the Z equals guy. So this here is G of XY. And the last thing you need to know is, what does this region, this surface look like if you projected it onto the floor, like if you made a shadow on the floor? And I'm saying this is a rectangle, it won't always be, but we need to find this guy. And what we've got is, this is our surface, and Z equals 1 to Z equals 4. So if you make Z1, that information becomes this. And if you rearrange this, you get that. And if you plug Z equals 4 into here, you have that, and that, when you rearrange it, becomes 16. So on the floor, on the XY plane, the place where D is going to live, it's between two circles. So it looks like this guy here. And that is our region D. Now, although I haven't calculated what this is a very big clue. Would you agree that we're probably going to do this in polar form? Would you agree this region is best described in a polar format? So now I've got all the pieces, let's put them together. Our surface integral of a vector field being integrated over the surface S is the double integral of D, negative P, the partial derivative of G with respect to X, take away Q, the partial derivative of G with respect to Y, plus R dA. P is negative X, so it's going to be negative X times the derivative of this thing with respect to X, which is a bit of a pain, so I'll do it up here. If you want to differentiate this function with respect to X, Right, think of that as being your g. You want to differentiate this, you're going to multiply by the power, reduce the power by 1, and then differentiate inside, which gets me another 2x. So I'm going to get the answer x over the square root of x squared plus y squared. So this guy is going to be x over the square root of x squared plus y squared. Take away q.
Wouldn't it be a positive x because it's a negative x and it's negative p?
Negative p, negative x. Thank you. And that's going to be positive for the same double negative reason. Now, if you differentiate this with respect to y, can't I use the symmetry thing? And that's what that would be equal to. And r is going to be a z cubed. Over dA. So I've got a double integral over d of x squared over the square root of x squared plus y squared plus y squared over the square root of x squared plus y squared. And now I've got a z to worry about. Well, z is this guy. Okay, z is this guy. So z cubed is going to be this guy cubed. Are we still okay? Right. So far, so good. Taking this as slow as we can. Now, what I'm going to do now is combine these two together and get x squared plus y squared over the square root of x plus y squared plus the square root of x squared plus y squared cubed dA. Now, since d is this guy, I'm going to do it as polar. And it's going to be a radius of 1 and a radius of 4. So we know that r is going to go from 1 to 4. And it's the entire circle all the way around. So it's going to be from 0 to 2 pi. So I'm going to do a theta equals 0 to a theta equals 2 pi. I'm going to do an r equals 1 to an r equals 4. This guy here is going to be r squared. This guy in the bottom is going to be r, plus this guy is going to be r cubed. And then the dA is going to become r dr d theta. So I'm now going to have the integral theta equals 0 to 2 pi, r equals 1 to 4. Distribute that and you get r squared plus r to the 4 dr d theta. And then that one is actually a pretty reasonable integral to do. Would you agree you could separate it and plug and chug and you're done? Are we good with that question? So probably you don't need every line that I did there, but just me being safe. But quite long questions saying that. So where's the next one looking like? Just doing it. Not really interested in there. Okay. Let's look at question 10. The vector field is x, y, z to the 4. Oh, no, I'm not doing that. 10 is too much like 8. You're not going to get anything new out of that one. I'll do 9. So 9 is a vector field. It's y, negative x, 4z. Okay. And S is a hemisphere, right, that's half a circle, half a sphere I should say, is x squared plus y squared plus z squared equals 4. And they're talking about z greater than or equal to 0. So if I try to visualize what that would look like, it's okay, not too bad. It's the top half of a sphere, right? Are we good with that, guy?
The limits would be like 0 to 2 and 0 to pi.
Definitely 0 to 2. So if you imagine what does that look like in the floor, actually on a floor isn't it a circle, a complete circle. So 0 to 2 is correct. You can tell that from here, can't you? The radius is 2. And theta is going to be everybody. And P and a Q and an R. So got all the necessary pieces. Let's put them into here. So the surface integral, also called the flux in this situation, is the double integral of d negative p dg dx negative q dg dy plus an r dA. Okay. So what do I have? I have theta equals 0 to 2 pi. I have r equals 0 to 2. I have a negative y. And I need a g. And the g comes from here, which means I'm going to have to rearrange this and then realize it's a square root. And so when I differentiate this guy with respect to x, I'm going to have to call it a half power. When I differentiate the guy with respect to x, which is the same thing as that guy, it's going to be 1/2 4 minus x squared minus y squared to the negative 1/2 times a negative 2x, and that ends up being a negative x over a square root. So this guy is going to have a negative x over that square root. And this fella is going, is that a y or a negative y? I better check that. What's the question? Yeah, that is a y. So this guy is negative of y, that's okay. And this one is going to be q, and q is what? Negative x. And the derivative with respect to y gets you a negative y over this guy. And add an r, which in this case is add a 4z. And since I'm doing polar again, it's an r dr d theta.
How is that z negative x over the square root?
How is that? Say that again.
How is z negative x over the square root?
I can't say a negative x over this. Oh, here?
Yeah.
Is that one? Right. So if you rearrange this equation, z ends up being this fella. And you differentiate this fella with respect to x, and you get this guy.
So that should be 1/2 that times negative 2x, not times 2x.
Check that with a negative here. Right, so I've got this guy, so I'll multiply by power, got it. I got this guy, take away 1, got that, times this guy, and that gives me a negative x. And so I'm not sure what I've done wrong. Have I done something wrong?
I missed, once again, I mistook a negative for a times.
Okay, we're cool. It's me being careless. Right, so you got this fella. Take away negative of that guy, that's this bit. This guy is going to be negative y over the square root, got that? This is 4z, got that. Okay, so it's 0 to 2 pi, 0 to 2. That guy's going to get me xy. Good grief. There's a negative, and a negative. So I'm going to get negative xy. You're breaking up, Sally, so I'm not sure what you're asking. Do you want to say that again?
Wouldn't the negative, wouldn't the y over x over the square root of the stuff minus
You're
x
breaking
y
up,
over the
Sally.
stuff, wouldn't that cancel out and become 0?
Right. It's probably my old age, but I'm not hearing what you're saying. I think if when you speak closer to the thing, it's a better signal for me. So one more time, please.
Wouldn't the x, y over the square root of stuff terms, wouldn't those cancel out?
Oh, these two? Yes, you're right. They will cancel out. Plus 4z. And z is the square root of 4 take away x squared, take away y squared. And then we have the r, dr, d theta. So I've got a 0 to 2 pi. I have a 0 to 2, as you say, they cancel out. And I have 4. This guy I'm going to call 4 take away r squared. And then I have an r, a dr, and a d theta. So by the time we've completed it in polar, this is what we're looking at. Are you comfortable with the 4 take away x squared, take away y squared becoming this guy? Right. Now, if I thought ahead, I would have actually written this line down. So I'm now going to do it. That's what we've got. Agreed? If you do this integration first, what method would I use to integrate 4r, the square root of 4 minus r squared?
That would be our good friend, the u sub.
Right, and if you do your u sub, off you go and do all your good stuff, and ... right? You can finish that. I don't know why we seem to be dealing with polar, but it just seems to be maybe that's the kinds of questions that get generated and come out nice. So just to prove that's not the case, that every question happens to be polar, here is question 12. Our vector field is xy 12x squared and yz. So there's my P, there's my Q, there's my R. And the surface is written down in a nice, easy to use form, which is that. And X is going to be from 0 to 1, and Y is going to be from 0 to 2. So in a lot of ways, this one is a lot cleaner because most of what you need is kind of handed to you. So the surface integral is going to be the integral from x equals 0 to x equals 1, the integral from y equals 0 to y equals 2, because that is essentially what d is. Then we're going to do negative of this guy multiplied by the derivative of this guy. So think of that as being what g of xy is. The derivative of this guy with respect to x, which is e to the y. Then you take away q, which is 12x squared, times the derivative of this guy with respect to y. And that basically gets you him. Plus a yz. So I'm going to have an integral from x equals 0 to 1, from y equals 0 to 2, negative xy e to the y, negative 12x cubed e to the y, plus y, and replace the z by x e to the y. And I'll do a dy dx. Anything I can do here? Let's see. I could pull out. I can't. Pull out an x, but I want much just. And then combine. Oh, just noticed it. Won't that guy get killed off by that guy? Right, xy e to the y minus xy e to the y. So we now actually have the integral from x equals 0 to 1, the integral from y equals 0 to 2, and the guy in the middle is negative 12 x cubed e to the y dy dx. And I would separate them. There's the x's. And there's the y's. Would you agree that probably integrates quite nicely now? Any questions about that one? Actually, that one's a lot nicer than the first two. Go figure.
Not to beat a dead horse from yesterday, but
Yeah.
I started thinking about the chain rule one that we did for integrating. I think it was like x plus y plus 1 to the half power or something.
Yes.
Sorry. If it were like x squared plus y plus 1 to the half power,
Oh, you'd be in trouble.
that would be really bad news.
Yes.
Okay, so we're not going to get something like that on our homework.
No.
Okay.
Yeah. Let's just pick one. Right. Suppose you were doing that. Now we're talking integrating with respect to x. You would call that 3x plus y minus 1 to the half power. And the rule is add 1 to the power, divide by the new power, and then you multiply by 1 over the linear version of this. So this trick that I'm using only works if that's 2x, 4x, 3x, x. In this case, you would end up with 2/9, and you could turn that back into square root of 3x plus y minus 1 cubed. You cannot do it if it had like a 3x squared in it. This question no longer becomes an obvious integral. In fact, it's not an obvious integral. It's not really anything we can do. There are lots of integrals we can't integrate exactly, and that would be one of them. Now, could I differentiate that? Not a problem. You can differentiate almost anything in the universe. If you had the time, you can differentiate. Integration is not the case. So that one, it doesn't work. And so the trick that I'm using can be used for other functions. If you wanted to integrate that guy with respect to x, you would get e to the 2x plus 3y minus 1, and this guy's derivative is 2, so you get an extra half. And if you wanted to integrate the sine of 2x plus 3y minus 1, again with respect to x, you would get negative a cosine of 2x plus 3y minus 1, and that guy would get you a half. But if you were asked to integrate 2x squared plus 3y minus 1 dx, the answer is you couldn't do it. Not a nice answer, but it's not possible to do that. There are many integrals in the world that you cannot do, and that would be one of them. Does that help?
Did you approximate that integral as a series and then?
Oh,
do
there's numerical ways of estimating it, right? There is numerical ways of doing it. So you could do it, you know, by breaking into little bits and adding them all up, you know, doing a Riemann sum essentially. But you would really want a computer to do that because it is really, really time consuming and not very, not a lot of fun.
Does this have something to do with elliptic integrals?
Which one are we talking about for an elliptic integral?
I was
Or
thinking-
just the term elliptic integrals?
Yeah, because a while ago I was looking at because you can't find the perimeter of an ellipse.
That's true, you can't.
And
Strangely enough, it should be possible, but no one's created one. They've only got estimates.
so what I did, it was like, okay, because I was in high school calculus at the time, and I just went and looked at the arc length formula we just learned. It's like, okay, I'm just going to apply this to an ellipse and see what happens. And sure enough, you couldn't solve it, but I put it into Wolfram Alpha, and it came up with an answer, and it said that it was an elliptic integral.
Right.
So what's going on there?
An elliptical, there are functions out there who are described in terms of integrals. So it's like a logical loop. I'll give you an example. I'm making one up. No one knows the answer to this integral. Right? It's not doable. Right? Let's say it's not doable. Could be proved wrong. I would call that the Robertson function. So the Robertson function is the integral from 0 to, well, I'll call it 0 to x of e to the t cubed dt. Now, once I've defined it that way, and someone says to you, I am trying to find 0 to 3 of e to the cubed dt, you will say, oh, it's a Robertson function evaluated at 3. I haven't actually integrated it, right? I haven't actually told you it's the square root of 2 plus 1, right? Haven't I only told you what it is in terms of what it is? So how does that function work? You plug that formula into a computer and you get it to do 1,000,000 Riemann sums, and it adds them all up and it tells you the answer as a decimal. So when you plug R of 3 into a computer, totally making this up, you get the answer that, and you say, okay, that must be the area from 0 to 3 of that particular guy. So the elliptic function is just someone has created a function that is in terms of integrals. There are quite a few. If you're interested in looking them up, here are some functions you can go looking up that are described in terms of integrals. There's a gamma function, and looks like a hangman symbol. You've got the beta function. I think, don't bet me on that one. I think it's just called beta x, but it might be a Greek beta instead of a b. That's the two that come to mind. Actually, the gamma function is very closely related to factorials. And you will find that integrals of things you cannot integrate can be given in terms of gamma and beta functions.
You know,
And,
this
so
gives you
elliptic
a-
function is just another one of those.
This gives you a much better appreciation of what all of those human computers were doing in the early days of NASA.
Oh, those poor guys, I would, oh God, I would,
Uh,
that job would have drove me crazy. Because
Most
one,
of
you have
them
to be
were women.
accurate. Yeah, I remember reading about it. I haven't seen the movie, but I do remember reading about it. You have to be really, really focused and really, really careful. Because, you know, if you're doing a calculation that involves you just doing it numerically by hand, can you imagine how a little slip could end up with the thing crashing into the moon? Because you thought a particular function's value was not the number you got. And it can simply just be a plus instead of a minus, couldn't it? And it could also be something more dangerous, like a
Metric to
factor of
imperial.
10, right? Where the answer's 10 times bigger than you thought it was. That would be, you would have a bad day on that question. Okay, let's
There-
pick one.
There's a book by a guy named Richard Feynman who was worked on the atomic bomb. He said when they dropped the first hydrogen bomb, they were kind of concerned that, you know, if we're going to fuse hydrogen to make this bigger explosion, what stops it from fusing the nitrogen in the atmosphere? And that'll create basically turn the entire planet into a giant hydrogen bomb. And so a bunch of guys whipped out their slide rules and figured it out with
Okay.
slide rules.
With slide rules. Right, here goes. Let's do one more to kind of put the icing on the cake. So let's do this fella. Keep forgetting to put that as a vector. I'll just write the formula down so I've got it handy because I'll need some space. And the guy I'm going to do this on is the function 3x plus 4y minus z equals 9. And the region that we're going to do it on is going to be in the first octant. Oh, and I need a vector function as well, don't I? And so my vector function is simply going to be x plus 2y plus 3z. Now I'll make that a square. Just to be-
I think
just to be
your
different.
projector freaked out. It's looking very purple or like blue.
It's
What's
not
looking-
like
Yeah.
yeah, no, it's just funny. Yeah, that paper is like unreasonably purple. It's not like it's not distracting at all. It's just funny.
I have no idea what you're saying. I see yellow and white, by the way. So this is yellow and this is white. So the fact that looks purple. Or
Actually, that makes sense. The camera is probably taking that paper and thinking, okay, that needs to be white. And so then because the other paper is a different color, it shifted that to purple.
okay, I could live with that. So for our final question, let's focus on D. D is going to come from here. So we did, I'm going to change my numbers just to make things nice. Make that 36 now. Right, if you want to find out where this crosses the x-axis, make y and z 0, and you get the answer 12. If you want to find out where it crosses the y-axis, make x and y 0, and you get 4y is 36, so that makes y 9. That's good. And since it's in the first octant, isn't that bit there on the floor, isn't that going to be D? Now, could I find out what Z is? Sure, I could. Wouldn't Z be some guy down here called negative 36? But I only really want to use it to find what the projection of this would be on the floor, right? And we have this guy here. And so if I orientate it, I now have a 12 here. And what number did I give the a 9 here, right? And so this is what D would look like when you kind of orientate it a little bit. And so I need to know the equation of the straight line because I'm going to do it with vertical strips. The equation of this line, well, it's 9/12, so it's -3/4 x plus 9. And so the y values are going to go from 0 to -3/4 x at 9. And the x's are going to go from 0 to 12. Are we comfortable about how we created D? Right. So we get an equation of a plane in 3D. We're being told it's the first octant, which it almost always is, isn't it? Because the questions, they make it that way. We figure out where it crosses the X and Y axis. We orientate it, get the line, we got that set up. So there's D. In this question, there's P, there's Q, and there's R. I also need to find out what is called G of XY, Z equals G of XY. If you take this equation, the surface that we're talking about, this fella, if you subtract 36 from both sides and you add a Z to both sides, can you see that we now have the G of XY that they're talking about? And I've deliberately chosen it to be very, very nice. So our surface integral, our flux calculation, is going to be the integral from x equals 0 to x equals 12, the integral from y equals 0 to -3/4 x plus 9. Negative p becomes negative x, and the derivative of g with respect to x gets you 3. Then the negative q is going to get me -2y, and derivative of g with respect to y gets me times 4. And what else have we got here? Plus an r, which is plus 3z squared. And we're going to do the y's before we do the x's. And the only thing I have to change here is I need to change the z's into x's and y's. So that's going to be -3x, -8y, plus 3 lots of z. What's z going to be equal to?
3x plus 4y minus 36.
Essentially G. Agreed? But at this point, I think it's worth stopping. Would you agree that's just going to be some really ugly polynomial in x's and y's? And you'll be able to integrate it. It'll probably take you a fair amount of time because there's a lot of pieces to it. And you'll get 42. And if you do, that's a total fluke because it's probably 1799ths or something, messy. This is it. Are you comfortable about the second formula that you're going to be using, this one here, to calculate these surface integrals? A lot of it is similar. Would you agree finding D is identical? Right, finding this region, same in all stories. This is the difference, right? This guy here. Didn't yesterday have a really ugly square root guy floating about? So you know that you've got a different kind of situation there. Secondly, have you noticed that today the surface integral is written in this form? And yesterday it had a different look to it. So hopefully you can tell by the way they write the questions which of the two methods that you're going to get. So if your integral looks like that guy, then that's yesterday's, isn't it? Right, that's what we did on Tuesday. And if it looks like this guy, isn't that today's? So the way the information is given to you is going to affect the formula that you're going to use, right? Doesn't this integral have a big square root stuff in it, right? And doesn't this integral have a negative p, a negative q, and an r in it, right? So they're quite distinct formulas. You couldn't really use this formula on that question, because here's the problem. If you try to use this formula on that question, who is P, who is Q, and who is R? Would you agree it ain't possible? There isn't a P, a Q, and an R, right? And if you had this formula, right, which would be, in this case, should be told a vector function, and it looked like this. Yeah. You couldn't use this information to figure out what goes here. So they're very distinct, different surface area questions. So hopefully you'll realize when it looks like this, do that guy. When it looks like this, do that guy. There is a